So if the compound is an acid on the left side, it would have to have a conjugate base on the right side. So if we look at the conjugate acid-base pairs here, we know that HCO3 minus would be the conjugate acid and would have a conjugate base of CO3 2 minus. And then the compound H2PO4 would be the conjugate acid of the base HPO4 2 minus. So this once again is the conjugate acid, and this would be its conjugate base. Conjugate acid and conjugate base. So sometimes you might get a question where it sounds kind of maybe confusing. Let's see if I can slide this over. There we go. So let's say you were asked, what is the conjugate base what is the conjugate base of, let's say, HS minus? So what is the conjugate base of HS minus? Well, if you're looking for the conjugate base of HS minus, that means HS minus must be the conjugate acid because you're looking for its conjugate base. So these compounds only differ by one proton. So if you were thinking HS minus, if that's an acid, if that could be an acid, then it would have to lose a proton and turning into its conjugate base. So sulfide ion would be the conjugate base of HS minus. Now, if we go back to the data chart, we can probably do this much quicker now. We can sort of see these patterns here. Let's close that down. So getting rid of that. So if we looked at, where is it here? IO3 minus, well, that's a base. So that would be the conjugate base. But what would the conjugate acid be to IO3 minus? Well, if it's looking for the conjugate acid, it must have one more H, so it would just be this compound. So those are conjugate pairs of each other. If you were looking at, let's say, HSO3 minus, and someone said to you, what is the conjugate acid of HSO3 minus? Well, that would imply that HSO3 minus is a base, and so the conjugate acid would have one more proton. So just like the example above, H2SO3 would be the conjugate acid of HSO3 minus. But what if someone said to you, what is the conjugate base of that? So what is the conjugate base of HSO3 minus? Well, that would imply that HSO3 minus is an acid now. And so if we take a look a little further down, we saw this one earlier in the example, HSO3 minus, if that's an acid, its conjugate base would be one less proton, which would be SO3 2 minus. So there's a few questions in the book that kind of word the question that way. And so if they're asking you to find the conjugate base, then they're kind of implying that that substance you're looking at is an acid. And if they say to try to find the conjugate acid, then that's implying it's a conjugate base. So let's say the question had switched. Let's say instead of saying base here, they said acid. What would the conjugate acid of HS minus be? Well, that implies HS minus is a base. So to be an acid, you'd have to have one more proton, which means H2S would be the conjugate acid of HS minus. So it's a lot of words, a lot of strange twisting the vocabulary around on you. Okay, so the last topic for today is strong acids, strong bases. Now, we're going to get more into this later on, but just this part's just to get you started on this. A strong acid is an acid that ionizes 100%. And a strong base is a base that ionizes 100%. So we're just going to write that definition down for now. A weak acid and a weak base, basically they ionize less than 100%. So pretty simple definition. If you ionize 100%, you're strong. And if you ionize less than 100%, you are weak. unless you don't know what ionize means. That's kind of a tricky word. So we talk about ionizing. We're talking about what the compound does to the water. So if we look at, say, something like HCl, and you place that into water, H2O, we know for sure that HCl is an acid, and it's going to form into chloride ions and hydronium. So that is the reaction there. Now, you might notice I put a one-way arrow here, and we've got to figure out how we know that. But before we figure that out, we should now notice that if it's a one-way arrow, that means the reaction can't go backwards. And so that, by definition, means 100% ionization. So the acid completely turns into that. So it's completely converted into that. Another compound that would show this, we could look at a base now maybe. So let's try a compound like NH2 minus. Not a common base for you maybe, but if you react that with water, that is also a one-way reaction. And what you end up getting is NH3 being made and hydroxide ions. And notice once again it's a one-way arrow, which means it goes 100% in that direction. There's no backwards flow here. There's no backwards here. If we take a look at a weak acid, let's just take an example of one we've sort of seen earlier. If you take a compound like HF and you react it in water, I'm liking all the colors I get to pick here. I should probably keep like a common theme though, maybe. But anyway, so let's say HF reacts with water. Well, we know that's an acid. It's going to go F minus and hydronium. Now, if you look at this reaction and compare it to the one above, the very first one we did, I've also drawn a one-way arrow here. So if I leave it like that, I'm implying that it is a one-way reaction, 100% in that direction. But it turns out that this reaction is not one-way. It's actually able to go both ways. And so that's usually what you see when we see reactions that are weak. Now, because HF is an acid, we call it a weak acid. So let's take a look at a weak base here. So I'm going to use NH3 as an example. And I can add it to water. And if I do that, it actually is also weak. It's going to be equilibrium arrows. And now NH3 will take a proton from the water, turning into NH4 plus and hydroxides. So the big difference here is that we notice that with weak, we always have equilibrium, and with strong, we always have one way. So that's a very important thing to recognize. So how would you know that? Like, how would you know HCl is strong, and how would you know HF is weak without memorizing every single acid and every single base? Well, this is where your data table comes in really quite useful. So if you flip back to your data table, I'm going to try to erase all these things I've highlighted from previous questions. Going up here, getting rid of that, get rid of that, go back to the bottom. I think I did some stuff down here. There we go. Okay, so let's start fresh here. So we said HCl was a strong acid. So let's look for HCl, hydrochloric acid. Well, there's hydrochloric acid. And we notice that reaction on data table shows a one-way arrow. So that suggests that it's strong. In fact, the first 6 chemicals up there, 6 acids, they're all strong acids. They can only go in the forward direction. So what about this NH2 minus business? Well, that was a base. So let's go down the base column. So we're going to look down our base column, and we're going to go way down to the bottom. There we go. NH2 minus. Okay, now notice the arrow is one way in the reverse direction, which means that NH2 minus can only go to the left, which makes NH3. So that means that NH2 minus is a strong base, and so is the oxide ion above it. O2 minus is a strong base, only goes one way. So that's why, or how we know that those chemicals are strong. Now the other example we did was HF. So let's see if we can find HF on the table. Now we said HF was an acid, so let's look for HF. There's HF right there. And HF, notice beside HF are these equilibrium arrows. So that suggests that HF can turn into fluoride, and fluoride can turn back into HF. So that means that HF will not ionize the water 100%. It doesn't turn the water into an ion 100% of the time. So it creates a nice equilibrium there. The other compound we looked at was NH3. And if we go down the table looking for NH3, where's NH3? There we go. NH3 is right there. Now notice it's under the base column, which makes it a base. And it also has equilibrium arrows beside it. So that would make NH3 able to turn into NH4 plus, but also NH4 plus could turn back into NH3. So we get this equilibrium being created